That's great. Okay, I think I'm ready to start streaming. It's scheduled. I guess as ready as I can be. Well, we are streaming. Go live. We're going live on YouTube. I think I'm gonna switch back to my earbuds real quick. I can now. Yep. I just had to. And now I'm not getting any echo, which is good. I just changed my Skype audio to use the earbuds out of the laptop instead of sending to the H6. I'll figure that out some other time. But we're good to go, Bill. As far as I know. Hey. Printed circuit board. How do I spell PCB? Yep. Yeah. There's still a few of them out there. I still hear it every now and then. It comes up a lot when you do IPC trainings. There's still a lot of people in those IPC certification programs that call it a PWB. It's kind of I never heard it in Australia, even since I was 12 years old or even younger, learning about electronics as a hobbyist as a child. It was always a printed circuit board. I didn't hear PWB till I got to United States. Oh, you turned me on in your room there for a second. Okay, because that's distracting me. I was just going to say, first time I came across the phrase PWB was after I moved to America in 2005, and someone called it a PWB. I'm like, it's a PCB. Oh, there is. Is that on YouTube or Facebook? So it does. I swear, people, we are definitely going to get this right. Okay. Tales from the dark side. No, I don't know. Well, actually, that is kind of one of my hobby horses, actually. You may not want to get me started on that, but people have been trying to use, I mean, since CAD was first developed on desktop computers, even since before that, since it existed on mainframes, people have created automatic routing algorithms. You know, way back in this, probably as early as the late 60s, people had put quite a lot of effort into the computer science of path optimization. And PCB design is a classic example of a classic use case of that. And yet designers have universally rejected routing automation and until now. And I think now they're using it every day. They just don't see it that way because it's very much user guided. But there's still a lot of people out there that think, you know, you should be able to auto route boards. And then we
should.
We try, and people inevitably hit a wall, and the router can't complete it. Maybe it gets to 96% complete.
Well,
and then
that's what I call auto routing. Yeah.
But it's like, you got to understand, if it takes a human weeks to route something, you can't expect software that's written by humans that can't cover all the corner cases or use creativity in the same way. But I think that's changing. I think artificial intelligence should get us there. And the latest routing engine with glossing that came from some very clever Russian dudes who have been doing this for years. Some of them came from I guess I can't put all the cards on the table. It's probably not the right thing to do. But some of them came from another company where all they did was focus on routing. And then the barrier is, if you want to do any angle, you've got to realize you've got to have a good engine that allows you to edit after the fact. I asked Charles File.
Right.
I don't know if anyone on the stream knows who Charles File is. He's a tremendous chap. He's retired now, but gosh, one of the nicest human beings you could ever meet. Just really chill and very knowledgeable about routing. He ran a service bureau, and he used auto routers when they were running on mini computers. He had a service bureau designing PCBs for many years. Then he got into EDA because, you know, and unfortunately he worked for Altium's major competitor for quite a long time. But eventually he came over to the light side and rounded out his career with us, and such a nice guy. But he and I talked about this, and he said the biggest problem he had when he was a professional designer running a service bureau, had multiple staff, with the automation was that you want it to be 90 and 45 for easy editing after the fact. But the technology's now gone beyond that. I think just in the last 2 years, the technology's finally gotten to where it doesn't matter what angle the traces are at. You can still push and shove things in a reasonably predictable, reasonably neat and tidy way, and it's getting better. So I'm really excited to see that. I think take for example the Topper router, which again is one of these. It's a Russian technology, and it hit the markets. Maybe I really became aware of it maybe 6 years ago, when an Altium co-worker of mine at the time, Rob. So hi, Rob, if you're listening, I hope you join into these. Rob is from South Africa. And Rob actually, at that time, or just before that time, was a reseller of Altium products for South Africa. And he also had reseller agreements with Topper, and he had reseller agreements with one or two other, simulation providers. Antenna Magus was another one I think he sold. And so he had access to this auto router that would rubber band all the traces at any angle, because if you actually go, and it reminded me of the days of point-to-point wiring with wire wrap. You know, whole telecommunications backplanes have been done with wire wrap before they got really, into putting a lot of PABXs or ABX automated branch exchanges, for the POTS telephone system. Huge buildings. They went from clunky mechanical crossbar switches that had to be literally debugged. They had to go through and clear the bugs out because they were warm and they attracted bugs at night. They went from that to more neat and tidy relay-based systems that crossbar switches built with relays that were in little sealed units and a lot more efficient, a lot less heat, but still pretty hot, to wire-wrapped boards. And the wire-wrapped boards were actually, by all accounts, extremely reliable because they had silver-coated wires and they had pretty decent signal integrity, even though by today's standards, the signal integrity would be darn horrible. But back then, by those standards and at those chip speeds, it was totally fine because they took the shortest path and they minimized inductance and they had very little crosstalk because all the wires were just at any different angle. And that actually prevented crosstalk for a lot of them.
It does. And we've got examples of wire wrap here. And the technicians would try and put them into channels. And I'd be tearing them back out of the channels to make it jungle routed. Yeah.
Yeah. So as humans, we tend to like things neat and ordered, and we have a propensity to try to make things all parallel and beautiful, and that looks cool. And I remember admiring, the Apple II. My dad had an Apple IIe before we got the first IBM clone. We had an Apple IIe, and I remember looking inside the chassis and admiring the trace routing on the board and how everything seemed all like real neat and at right angles and just beautiful. But we all realize now any angle is far better for signal integrity, especially if you've got some plane layers in your board. Yes, I see the C128 motherboard. I'm gonna
talk about poor signal integrity. This is it by today's standards. This sucks. Yet we got it to work.
I'm making you full screen so the folks on YouTube can see it a bit. Hold that up again, real close. It looks like you've had some heat sinks on a couple of those devices.
Well, this is yes, because normally there is a metal shield that allows us to syn, right? And it's an EMI shield, and it's needed. So then we dropped fingers and put heatsink grease, and so the application of the heatsink grease cost almost as much as the shield, because any manual operation times 7 million is a lot of operations. So yeah, but we wouldn't have had to heatsink them if there wasn't a shield, because most people don't realize the PC board is actually the heatsink for most chips. It's at least 60-70% of the heat generally goes through the lead frame of the chip into the board. It's not radiated off the top unless you're overclocking like you see in GPUs these days.
Yeah, and actually PCBs make terrible heat sinks, just so you know.
They do, and yet still 60-70% go that direction, right? So
yeah.
Our job as chip guys, I'm not a chip guy, but I worked with the chip guys, was to get it to the lead frame, and then I'd say, I'll take the heat from the lead frame. You get it to me, and I'll take it somewhere else. Because heat doesn't go away. You just have to move it, right?
Yeah, and even today, there's a lot of motor drives, Class D audio amp chips, even analog. I remember the LM380 when I was in college doing a little stereo.
386.
The 386 was the smaller one, but there was a stereo version which was the 380.
That's right. Right.
And in their National Semiconductor app notes, they said all the heat comes out of the center 6 pins on the 14, or I think it was a 14-pin dip. So the middle 6 pins They said if you're going to drive this at full power, you have to attach a heatsink to these pins, or put a huge copper plane coming out of them to help dissipate the heat. And that thing did actually get quite warm. But
and that's because it was a Class A amplifier, not a Class D like we have today, right?
I think the 380 was a Class AB.
Okay, I almost said that, but I was trying to stay simple. Well, okay, you said it, so let's talk real quick. That's the whole purpose for getting together here. Class A is where it's just a straight amplification, but we run into problems with how much can we do with a single transistor and its cutover points. And Class AB is what?
Well, Class A is that all the output devices are continuously conducting in their linear region.
Good description, yes.
So a Class A amp may still be a push-pull amp with an NPN or an N-channel MOSFET at the top or at the bottom and a P channel at the top, or vice versa.
Or it could be a single transistor. It could even be a single transistor too.
And this really originated in tube amps, and there's still a lot of guitar amps out there that do this, where you have a single or two tubes in parallel for added power output, driving single-ended, driving a transformer for impedance matching at the output, and the transformer has enough DC resistance that allows that to also be the middle bias point. So you have one or two tubes, electron tube valves, we call them in Australia and England,
yes,
as the active devices, and they're putting out tons of heat because they're biased on all the time. And the transformer, the output matching transformer, is also putting out tons of heat because the primary winding is using a combination of its inductance and its DC resistance as the load for the Class A output stage. Yeah, something
By the way,
like that. And they
when
get
we
real
say
hot.
transformer, we mean transformer, right?
I like that. That's a real, yeah.
I can light a neon light bulb with this and a 9-volt battery easily. That's how much energy you can store in there.
Did that come out of a microwave, or is that from something else?
That's just a regular old polyfilament transformer. I traded doing a show for somebody for the transformer. When we were done, I was like, can I have the transformer? And the library gave it to me. And then I used it for a Hackaday video to show inductive kick. Because we used to have these, I used to have a box of these, and now I can't even find real transformers that are, Oh, hey, so here's a good question. What are these little serrations in here? Why is this layers of material?
Well, that's an EI core. So those are soft iron or wrought iron, which has a nice high permeability. The problem is you get eddy currents. So
and the lamination breaks up eddy currents then.
Yeah, so it reduces core losses. Now,
That's
right. in modern switching power supply, now I have something similar just to show you. This is my, this is on your side on Facebook. I'll just hold it up to my camera. These are audio transformers, and they have the same structure, but they're obviously a lot smaller because they're not for transferring high power. These are for audio line level isolation. But these are nice and shiny. They're not the dull gray of...
Hold it up to the other camera. Yep. So right. Those are audio transformers.
Yeah, and these are cheap ones, but they're still very expensive. Transformers are very expensive nowadays because the whole world's gone to switching power supplies and try to make everything as small as possible. And so the cost of ferromagnetic materials for high-frequency devices has plummeted, and you can get really good switching power supply transformers and inductors dirt cheap. But now traditional transformers cost a fortune because they're very, very heavy and full of a lot of metal. And metal's expensive.
And shipping the metal's expensive.
Right, but you can't have heavy metal without a good transformer. Just saying.
There's a joke in there somewhere, but yes, you need that mass. And mass is just like it sounds. It resists a change in current until but then it becomes a source of energy after you've put current into the coil.
Yeah. So people ask on a lot of audio forums out there, why are audio transformers and why are tube matching output transformers?
Oh, you know what I would do different?
Why
Not
are
to
they
cut
so
you off.
darned expensive? And it's because the good ones use permalloy laminations. Permalloy is a
Right.
special alloy that it actually reduces the inductance a bit, but it reduces the capacitance of the coils quite a huge amount. So you can get a really big frequency response. If you get a transformer and design it to go from 20 hertz to 20 kilohertz, that's actually extremely hard to do. What were you going to say,
What
Bill?
I was taught to do different, hold up your board again. Now, I was taught to turn one of those. See, I'm on the other camera, but I was taught to turn the one of those at 90 degrees to the other one.
Yeah. So the stray magnetic fields don't couple, right?
Right. And so even when I cook hot dogs in the microwave these days, I'll turn the hot dogs at right angles to each other. Yeah, because the way I envision, it going through the... And if I had to put a third hot dog, I would stand it straight up, or make some kind of... But I saw 3 transformers one time, and that's what the designer had done. He put one at that way, and then one on the side in the third dimension, just so he could put 3 transformers near each other.
And the same thing goes for if you're designing a speaker crossover and a passive speaker crossover with coils, or same thing goes if you're doing a switching power supply or regulator design and you want less inter-output ripple. Like if you want loads and ripples on one 12-volt rail to not affect your 5-volt rail, you should consider the positioning of your filter coils to be at right angles as well. It makes the PCB maybe slightly larger or harder to design, but you'll get far better performance electrically.
So I'll ask you the question then.
Okay.
How do you... there's an EM field. We like talking about EM fields, you and me, especially at high frequencies, right?
Yep.
And an EM field is electromagnetic. So there's an electro and a magnetic part. And if you've seen the field lines, how do you tell right away which is the magnetic? Do you know where I'm headed with the question?
You look at your actual conductors and use the right-hand rule.
That's the way, but the other way, and you're talking about this, I thought it was, we call it the left-hand rule here above the equator. You being from south of the equator, it's probably the right-hand rule, but yes. But the other one is the magnetic ones, it's Coriolis effect, folks. The other thing is magnetic field is circular. So if you see the conductor and it goes all the way around and the ends meet, that's the magnetic field. And it's the electrical field that does the branching to the ground return plane. So the first thing I do is I find the circular part. And when you envision that circular part going like this around a conductor, you realize that a probe like this doesn't go like this, it goes like this because you're trying to capture the round part of the wave. And this is a near-field probe, and we're going to talk more about these because we might talk about how to make a near-field probe.
Heck yeah.
With printed wiring boards.
Heck yeah. That's definitely a topic for an episode.
You call them valves, but not printed wiring boards. What? I mean, come on. What gives? They still called V on old schematics. You'll see a V1, V2 for valve.
Yeah, because that's what they are. They're valves.
They're valves.
That's exactly what they're electron valves. That's what they do. And they have...
So an FET is a quantum effect valving. Yeah, you're right.
A field effect transistor should have... There were probably many arguments between its inventors that they should have called it a valve because it operates in exactly the same way, just in silicon instead of in a vacuum. And without the heater, it relies on electron mobility in doped materials instead of requiring a heater to make electrons all jiggly and want to jump off a piece of metal.
Keep going. Tell us keep talking about what a tube does. You just said that the cathode, there's a heater on the cathode, and it excites electrons to jump off the cathode. What's it hit next then? And where is it going, and what controls it?
The electrons can't jump off just on their own. They are negatively charged particles, so they need a place to go, which is a place where there is a lack of negative charge. In other words, a positive charge. And that's so without a voltage across your anode and to cathode, to bias the tube on, you can heat up the cathode all you like, and the electrons will be whizzing around inside the hot cathode, but they'll stay in it. But as soon as you apply a voltage to your anode, that provides the charge difference that makes the electrons whiz off into the vacuum towards the anode. And then, of course, a simple triode tube has a grid in between the anode and cathode, and that's just a piece of metal mesh. And you can actually, if you can visualize this, the tube is using electric fields and electric field potentials. So this is getting into electrostatics here. But the grid, if you apply a negative voltage to the grid, it forms a barrier to the electrons whizzing off through space towards the anode. And so you can control the amount of current with a small voltage bias, and that's what gives you the gain in a vacuum tube. Bill, we were going to talk about Altium designer tips too, and we're nearly at a half-hour point already.
Wow. Okay. So one thing I was going to say real quick then, there's a transformer I had made because you can't buy them off the shelf anymore, and this is really just nothing more than a 9-volt center trap transformer. I had this made as a sample in China, and I would have had to buy 100 of these to buy one, right?
How much did that cost you? Because if you look at
free.
custom...
I just paid for shipping.
No joke. That's awesome. Because it's actually, you look at custom, if you want to design a special power supply, really, if you're doing a switching power supply with a common current or common voltage, there's pretty much off-the-shelf parts now. You're Worth Electronic, TDK, TDK Epcos, all these companies that make magnetic components have huge, Coilcraft is another one. They all have off-the-shelf parts. So they've already done the hard work of designing the magnetics for you, which is another topic for another day, is switching power supply design. It doesn't have to scare you. You can actually use...
I think it should scare you, but then you proceed carefully and cautiously and ask lots of questions. But that's just me.
Well, yeah, but all I'm saying is people get stuck. If it's not their forte, they get stuck at the magnetics design stage and give up and think, well,
right.
can we buy an off-the-shelf power supply that does what we want? Well, maybe that's not always suitable. Maybe you need additional insulation requirements or whatever. But most of these magnetics companies that make the cores and sell the bobbins actually will also have huge arrays of off-the-shelf parts that will be suitable for 99%.
You would have thought I could have got a 9-volt center tap. It's basically a 1-to-1 with center tap on one side, and yet I still had to custom make it. But you're right, they had an off-the-shelf core, and so they just set the number of windings, ran it, and dropped it in a box to me. And again, it would have cost, they could have run 100 in like 10 minutes. But
you'll have to share me the link to where you got that, because if I want to get a custom transformer wound up, I want to be cheap.
That's it. So before we get back to Altium, I ran to find my old RCA tube manual, and I didn't find it. But I'll have to pull that up because I was going to show a tryout. But what I did find was my old hardbound TTL Tektronix data book. So we'll have to do a data book show someday.
Yeah,
but
absolutely.
This back when data books. See, and you can tell I'm old because I say data book instead of data sheet. So.
And that's actually the wonderful thing about the electronics world is there's always enough of us to keep the old technology going and alive as a boutique thing. There's always going to be, so we were talking about tubes. Actually, for high power radio transmission, we still use electron tubes or, thermionic tubes, valves, whatever you want to call them, because we can't make semiconductors that can cope with the voltage stresses and the power output levels that are required for high power radio transmission. It's not possible to make semiconductors that can do it today, but it is still current technology for that is still tubes for many different types of transmission. So, and then of course there's always the guitarists like me who want tube amps and things, and audio purists who want tube preamps for their hi-fi. So it's all good. There's always something to learn, and the cool thing about it is there's always books you can get. I've found a number of really awesome books that both old and new, that are widely available if you want to learn about these niche technologies. So it's fun.
So
it's fun.
Real quick before we get back to Altium, Facebook, I'm sorry, when I restarted the feed, I forgot to set you to public. Now you see us again. You missed a great conversation about tubes, custom-made transformers, big transformers, other things. But our Altium tip of the day is local grids, right?
Yeah.
Oh,
Yeah,
hey, there's a contest coming. I want to mention it before I forget.
Yeah.
You guys are having a contest, and you get a free Altium if you win the contest.
Is that it? I'm hearing this from you for the first time. So
you're getting a free Altium if you win. We'll have to get the link. We don't have titles yet, but we'll get titles so you can see the link.
Yeah. I'll add a link to the YouTube description after we end the stream. I'll put links in too. And
okay.
Bill, if you want to share me the links to any other related websites of interest or articles you've written as well, like that transformer, maybe give us the link to where you found that, and and we'll pop that link in below after the stream's ended.
Okay, let me interject real quick, and then the rest of the show is yours. And somebody just asked about the 128, so I want to talk about what we will talk about, because this is an old 128 board. It's 35 years old, and you can see there's a wire on here. And that's just how much this layout sucked, and yet we still managed to make 7 million. And there was a reflection. That's all I'll say for now. But what we have for the first time in 35 years is a brand new C128 board, and I'm going to recreate that reflection that I fixed with that wire and actually put it on the time domain reflectometer and see why. There's two processors, and it's only on one of the processors did the echo hit wrong. So that'll be fun.
I'm very much looking forward to that. Hey, I got a question though. Those new boards, were they from the original Gerbers or original production image?
He stripped down a PC board, scanned it, turned it into a DXF.
Oh my gosh!
Hours. His name's on the board, and rightly so. Let me give him a shout out, and then let's talk grids.
What a champion! That's a lot of work.
Yeah. I forgot I can't read that small. Johan Grip did this.
What a champion, Johan!
And even still put our names on as having done the original, so that was classy.
The retro computing geeks of the world, including me and Bill, salute you.
Yeah. Though we think you have entirely too much time on your hands, so let's be clear about that too. Local grids.
Yeah,
show us, what are we talking about?
Yeah, I'm going to switch to my desktop. So here I have. This is a design I did actually when we introduced the concept of local grids. And it's got a simple analog input, a low pass filter, an ARM.
I don't see your desktop yet.
Oh,
on Skype.
I'm sorry. We can see it on YouTube, but I forgot to share it with Skype. I am very sorry, Bill.
Not a problem.
These are the little things we're going to be finding out as we go. So let me switch to.
My first call as an EMT wasn't perfect. Didn't kill anybody either, but.
Now I can't find Skype in my applications here.
I hate software. Have I mentioned that?
Yeah, you have.
Oh, did I tell you my lifelong dreams to be a lumberjack instead of this stuff? Up in the trees of Great White North, North Britannica.
You must have been a Monty Python fan. Skype's kind of just vanished off my system, even though we're still on a call. Let me try and get
I had a Skype problem the other day, too. Is it in the tray at all?
No, it disappeared from there. The call is still there, and I got you back, so we're good. But I'm just going to share my screen.
Yeah. Can you hold it up? Oh, you can't even hold it up to the... Hang on. How can we fix this?
No, I'm sharing my screen now. So
there you are. There you are.
Okay.
All right. Start talking, and I'll bring it into Facebook here.
Okay. So you can see my screen there, too, on the Facebook side. Okay. So this is a reference design I did for highlighting the usefulness of multiple overlaid grids. on the PCB. So this is just a simple design. We take an analog signal in. There's an ARM microcontroller that has some analog A to Ds built in and a bunch of LEDs. And the code is to be a stroboscopic tuner.
Yeah. Depending on where you're north or south of the equator, yeah.
Yeah. So the idea is it compares the baseband frequency of the incoming signal, which might be a guitar input, or it might be a microphone hooked up in front of a violin, and you're tuning up.
Depending on whether you're north or south of the equator,
So the idea is it measures the frequency and beats that frequency against the reference for the actual note you're supposed to be tuning to. And the difference between those creates a slow-moving clock that cycles through the LEDs. So if the LEDs are moving slightly to the left in a ring, it means you're flat. If they're moving to the right in a ring, it means you're sharp. And when they stay still, you're in tune. So that's how stroboscopic tuners work. You don't need an ARM microcontroller. You could do the whole thing with 4000 series logic chips, and there've been plenty of designs out there in the hobby land that do that. But this is the board. And so you'll note immediately, I wanted to place the LEDs in a perfect ring. I wanted to place the LEDs in a perfect ring, and in older versions of the tool. So this was actually introduced as far back as AD10 in 2011. We released this. In older versions of the tool, you'd have to do your trigonometry and calculate the XY locations of the LEDs and place them by manually typing in the XY coordinates. And you'll see I've got my board reference is this circle in the very center of the middle of the main microcontroller in the middle of the board. Let me make those polygons.
Make the grid be more pronounced and your polygons less would be my advice.
I've just put the polygons.
Perfect.
So how you get to this, I hit G and go to the grid properties, and the current grid that I am working on will show up here. So this is the basic regular Cartesian grid. And I actually like to make it make the fine grid. I actually like to make these lighter normally. So let's make those a light green and make it dots.
And the main thing is that there's still a global grid, and you're just adding a local grid to help you with a portion of the board.
That's correct.
Yep, and that is cool. I did not know about that until I saw my friend Terry Fisher doing it. Fish, we call him.
Right.
Yeah, so I just learned that this week.
So this is my fine grid, but you can see here where the LEDs are, there's a ring, and that's a polar grid. And I set that up so that I knew I had 8 LEDs and I wanted them at fixed angles. So that's a 45 degree, 0, 45, 90, etc. And then also at a 45 degree offset and centered on the board origin, which is the current snap origin is the middle of the board. I have a Cartesian grid, which is rotated. And so,
right.
And these other big lines you see in my workspace are another thing that's really handy for precise placement of objects. You can see I've got a couple of horizontal ones there. Those are called guides. And you don't need those for aligning things. I happened to use them for alignment.
I use a lot of guides. I probably have about 20 on my current board, if not 30.
Yeah. So in AD 18, 19, 20, 21, which is not released yet, you go to the properties panel with nothing selected, and you get the board options. That's the key.
Nothing selected. Yeah.
You control snap. So one of the things people run into with grids and guides since the properties panel was invented in more recent editions is that by default only grids is enabled. And so you'll be trying to align two resistors together or align them to a guide. You set up a guide and you're like, why won't it snap to the guide? That's really frustrating. It's because
what I don't like about the guides is you can't turn them all on or all off at once that I could find. If you have 40 guides, you're sitting there clicking 40 times in front of, whoever you're showing it to.
Well, I would group select here.
Okay,
Let's see if I can do that. No, yeah, you're right. We need to fix that.
See, I used guides because I didn't know about local grids. So Altium, like all CAD tools, not all CAD tools, but good CAD tools, is there's more than one way to do something. So I was just doing it different, but on my next project, I'll use grids instead of guides, at least to start. But
yeah,
go on.
So, but they're both here. There's a grid manager and a guide manager, both in the properties panel. But just be aware that they only show up as board options because I've got nothing else selected right now. If I select a part or an object, the properties panel goes to the old, like what previously was called the inspector view, is basically the properties of the object that's selected. So you deselect, Shift C, or click in the blank space, then you'll see the grid manager and the guide manager. And this is actually, I don't know if we can cut and paste into this table yet, but I think that would be a really cool thing to add. So if anyone from R&D is watching the stream, hopefully, you take that on board. If you had, particularly for guides, if you had an Excel spreadsheet handed to you by a mechanical engineer with exact locations of screw holes,
which they do,
or button holes in a panel, you could have it. I mean, you can actually have the components placed based on those. You can do that with the list panel. You can import spreadsheet data, and that's another thing for another episode down the track. But being able to create guides for those point guides for those locations would also be very useful. Yeah, so grids are in here, and LED placement. This is you see it's there's two checkboxes. It can be enabled for non-component objects and for component objects. And actually this one ought to, probably when I was placing the parts, it would have been enabled for components. But so grids can be set up so that they're only applicable to components or only applicable to anything that's not a component as well. So there's that extra layer of usefulness to them. And the properties of this LED placement grid, it's I've got light blue, dark blue, all lines, and my angular step is 22.5 degrees, so half of 45. The radial step, that is from the center, the grid's going out from the center of the radius of the arced grid is 20 mils. And there's a start angle and end angle. So you could just have a polar grid that only goes for a certain pie slice. And it's pretty flexible. And where's the origin? Its origin is at the center of the board, 0, 0, which is it's not the absolute origin. That's my movable origin. And there's a start angle and end angle. Relative origin. That's what whenever you see origin in a field in Altium Designer, it means with reference to your relative origin, which is the one you can move around. So you can even relocate these things based on where you put your origin. The radial range, this is the innermost radius distance for this grid. So I've got a big space in the middle of it, which is not polar, and I've got a different grid on there. So it's just a thin strip that goes around in a circle. And we can see that when I zoom in, that's that polar grid. So super, super useful for doing things like front panel designs where you need, particularly for LEDs and switches and dials. If I were doing my Neo pixel glasses, this would be a very handy tool. But you can use it for copper objects as well. And these grids, needless to say, RF engineers love them too, because it allows you to precisely place copper. If you need to be exactly a quarter wavelength around an arc, this is how you do it. Well, one way to do it. I would also do that as a component. So I've got another grid here. This is the U1 grid. And this one is a Cartesian grid, but you can rotate it. So you can also have an angle, and it could be any angle, and you can say from its origin, how many quadrants is it valid in? So this one's all 4 quadrants, and that means I've got this quadrant, this quadrant, this quadrant, and that quadrant there. And then, of course, just for fun, I might reroute this board and use the new any angle routing automation and see if it probably will do a nicer job than what I did by hand.
Yeah, it kind of looks like the Hydra symbol off of the Marvel Universe here with the kind of the... That's really cool. It looks very flowy, right?
So that's the multiple overlaid grids, and it's extremely useful picture. And I don't know, Bill, we've been going more than 45 minutes now, so I think we probably should wrap this show up. But did you have any closing comments?
Yeah, I wanted to show you one thing since you mentioned front panel design. So I just happened to grab one of these, and this is where I used Altium actually to make an end panel. And so I can do silk screen, I can make any size, shape, hole I want without having to worry about a Greenlee punch or whatever. And then I happen to make this on an aluminum substrate PC board, so it's actually good for RF and whatnot. So I've started making my own front panels with printed circuit boards, printed wiring boards, right?
That is a most excellent tip. And
yeah, I love that.
I've been doing that as well, but I never thought to actually get an aluminium. You say aluminum. There it is again. North hemisphere, southern hemisphere.
Well, you know what? Where I think this happens is the Coriolis effect, right? When I hit the space bar, I notice all my objects rotate clockwise, and my theory is that when the people wrote this down in Australia, that it rotated counterclockwise when they hit the space bar.
It could well be.
We need a test to prove that someday. Go flush a toilet or something,
Yeah.
So, sorry, I knocked you right off your rocker, didn't I?
You threw me off. But that's a great tip. And so do you have any suggestions for, I guess pretty much any board house these days will do aluminium PCBs.
I did this with PCB. Yeah.
And there's still a layer of insulation and then a silk screen. And if you wanted, you could have copper on there as well and have parts mounted.
Yeah, and that's got the regular hassle finish, so that when I tighten down my SMA connector, it'll make good contact. So
I like that.
And that's how I had to do this to do USB holes, because up until then I always made them drillable with a drill. But if I want USB, whatever that shape is, I had to do this. So. All right.
Makes sense.
Well, we had a few technical difficulties. I think I had more than you this time. And Facebook totally got hosed. My apologies, Facebook. But anything that you would say in ending, other than we need to find a way to get the links out to all the things we talk about. We'll be doing that offline.
Yep. So we'll follow up on the Facebook thread and on the YouTube description page with links of the things we discussed.
Right, and some other time we'll show a Kim 1 board.
Oh, very cool. Yeah, we need to do a whole retro computing episode, because I've also got a few of my own little projects where I've designed things. And we started out today talking about auto routing, and I actually designed a board in Circuit Maker just because I wanted it to be open source and I wanted it to be accessible to anybody if they wanted to fool around with the auto routing. That's Altium Designer, of course, is extremely far more powerful now. But there's the basic Citus routing engine is available in all of our products, and I wanted to design a board that would lend itself towards learning how routing algorithms work. And that board is now it would be considered retro computing because I put an 8051 on it.
Yeah. Hey, you know what? I've got a couple different CAD packages. Let's have like a cockroach race only with auto routers.
Oh, okay. Yeah. It's
Well,
not just how fast it does the job, it's how good the job is.
Well, you're absolutely correct. It's how well does the human, in what position is the human in to finish that last 5%? You know,
Yeah.
is the board trashed or not? Is really
Yeah, do you
by the
have to
time you
tear
get
it all up and practically start again,
to
or
do the
can you
last
actually,
5.
can you actually just do the last few traces and call it good?
It took us 3 days. How many hours is that? 36 hours? No, 72 hours to do
72.
the last 20 traces of this. It was 3 shifts starting on Friday, going till Sunday night. And it was 3 shifts of designers, and then I was asleep on the floor in my army sleeping bag on an air mattress, and they would kick me in the foot when it was time to like wake up and make a decision. And it was so cold in that room that I took the McEgg things from McDonald's, put them on the shelf on Friday, and I ate them on Sunday, and they were still good. That's how the old refrigerated rooms that we kept CAD stations.
Well, I don't know. I think anything from McDonald's will last months unrefrigerated.
Except the cheese, yeah.
Except it won't taste good, but so
well, I didn't want to risk
one
it
last
till after
question
the
I have
board
for
was
you.
routed. You know, I didn't want to get sick in the middle of it
Yeah.
and then miss the schedule for that reason. So I ate it after we hit our milestone.
One last question I have though about that. What were you using to design the C128 Psi cards? And
Yep,
did anyone ever stop to consider, hey, we could create our own or get one of our development partners to do PCB design tools that'll run on the Commodore 128?
That's like having a paperweight, a doorstop, you know, run something. It was cute 30 years ago, but let's use gigahertz if we can.
I'm not suggesting
sure, we can slow it down if you want to.
I'm not suggesting we do it now. I was just thinking, did anyone consider it at the time?
Oh, well, Hedley Davis wrote the compiler that we used to compile the C128. He wrote for the 128 then, and so we used to use 128s to compile 128s, which is every bit as incestuous as it sounds. It was just warped.
Well, but that's no, like,
but it took
that's
a
how
VAX.
software developps now.
Right, but it had been a VAX. That was the point, was Hedley then took the VAX code and put it into a 6502 that could compile itself. So it was YAC, yet another compiler. Yeah.
That's a mean feat.
So,
yeah.
All right, let's wrap it up.
Okay. It's good talking to you again, Bill. Thanks very much.
Yeah. We'll do this more and we'll figure out more. I like the retro stuff and the Altium stuff, and I like pudding too, so
there's never a dull moment. And I'm excited because I got a new test instrument this week, but I won't say anything about it. We'll save it for another episode, but I want to go through that and talk about that sometime as well.
Well, I'm going to call you right back after this. I want to ask you about that. I promise I'll only take 1 minute.
Okay. So, thanks, everyone.
Bye, everybody. So, and here's where everybody gets to watch things get